me a little bit. There's one interesting side story you guys want to hear.
Yes.
Sure.
So he helped me with the grading, and he used a pencil. And in some of the problem, I realized later he wrote the answer into the writing. Now, a lot of you guys, almost all of you guys, write your exam paper with pencil, right? So when I checking through, then I was like, it doesn't make any sense because the answer is correct. Because I saw there's the answer right there. So I was like, no, I'm gonna correct this. So I add the points from the points he knocked out. Then later, I feel like as I'm reading more and more, I was like, it doesn't make any sense because I see the same writing from different papers. Then I realized, oops, that must be his. So I go back and change it. So you guys can see the question A, there's like a full point, there's like, nope, minus something right there. Okay, so I'm gonna tell him, I see he's being conscientious about this because he knows that I'm gonna looking through it, he wrote in the pencil that I can erase it, but, so you're gonna see the two components, the red mark is from me, there's a pencil mark from him. I look into actually every single problem, even the one he graded. So if you guys have any questions, I think the average is 75. I have a bonus point. I don't recall, but anyhow, I gave you guys all, since I wanted that bonus point for you, even you do not want it, I just added. Does that make sense? So if you look at your exam paper, and you look at what is posted, if there's a difference of 2, that's what it is. But that doesn't mean next time, that's gonna happen. This time I just give it to you guys, all of those. Okay, and then the homework 4, as usual. I know when I was a student, I like to do a little bit evaluation, how I was doing. So this will be due. I think it's better to have some sort of exercise or homework, okay? All right, so the schedule for today, we're gonna go through our lecture a little bit. Then I'm gonna allocate some time and go through it because the exam one is related with the foundation of quantum mechanics. So although later exam you'll be the application, but the understanding postulate, the foundation of quantum mechanics is really important. So I would like to spend some time and talk about it, how we approach this problem, how that relate to what foundation part of the quantum mechanics. You guys know how many times I taught this class? Yes? I've been here since 2007.
At least 3.
We rotate. Our faculty member rotate. So I taught many, many times, and I realized that, used to I don't have job. So I have 3 exams, and then 1 final exam. Then later I realized, sometimes take us, including me, a little bit to get the momentum. So for a new field, new discipline, we need that time to get what we want. And that's the whole point I had this job 1 midterm test. All right, so therefore, for those of you who would like to use it, I'm giving it to you. So, but the university want us to give you guys alert and alert and alert. You guys know that? Like the deadline for alert is October 6th. And I haven't finished grading the midterm exam yet. They already reminded me, hey, by the way, you haven't done that yet. But I would imagine you guys are very responsible for yourself. You're checking, make sure everything is going the wrong way. I'm not entirely sure. I'm not complaining about the administration want to make sure that I send out the alert, but fundamentally, I think you guys, this is really needed. So I need to give you guys an alert. So I did. So that alert is exclusively based on what we have so far. But if you look at the syllabus, we can drop 1 exam which jump to 0. We can jump homework assignment. So in that regard, you can think about if you didn't do the way you wanted, you really have all the opportunities from now on. That's all I'm trying to say. But I'm giving the alert based on your current credit. That's it. The other thing, if you feel like there's a grading error or grading add points wrong, I usually help out my TA because they have other duty, they have classes. So I would like to take that to myself. So basically, you can return the exam paper to me because toward the end, he graded all the homework assignment. I don't really know how he graded. Maybe I gave him the solution key and talk about it. But the exam paper, I know each problem, myself. So I would like you guys to return back to me, and we can go from there. Okay, now let's get started. All right. Okay, so we move on to the understanding for the second motion, that's vibrational motion. Particularly the model we are using. Is a simple harmonic oscillator, right? So basically, when you have it in here, because you can create, because a lot of situations, if we think about the chemistry as a bond, it's really an anharmonic. Now we can make it, if you understand the situation with a harmonic, we can introduce approximation, extend from there. So as a starting point for understanding the vibrational motion, we take an easy route. So we think it's a simple harmonic that is subjected to the restoring force, and then the force is linked to the displacement through the Hooke's law. The force equals to, guess what I have in my pocket today?
Oh,
Oh, 3 of them. At least one of them gonna work, huh? All right, so the force will equals to the proportional to the displacement with this constant magnitude spring constant. Now, for us to understand, you needed to get a relationship with the potential energy. That's how you generate your Hamiltonian operator. Now, for this simple harmonic, knowing that, and we went through all of those, resolving for it, we have energy expression, we talk to basic depths, and we apply to one particular problem. Now, here is the solution for the wave function. This is much, much more complicated compared to the solution to translational motion in 1 or 2 dimensions. So, long story short, this particular wave function also defined by your quantum number through the boundary condition. You have a whole series of solution, and you denote by the D, that is your quantum number. So that defines your quantum states. All right, there are 3 components. I wrote it out for you. The first part is the constant. That is the normalization constant. All right. Then you have the second component in your solution for the wave function. It is a polynomial in the x, which is your variable. And then you have the third component, that is your Gaussian function. So if we keep it going, so let's take a look at this. We can write out all right, so the wave function have a whole series. P is your quantum number. Now, guys, what is the P value?
sure.
Oh, that's your quantum number for vibrational motion. So we start from
0.
0. Very good. All right. All right. Now, if I say what would be your ground state?
0.
So then you're gonna write out the wave function, the vibration motion in 1 dimension. We define the dimension in the x dimension, and then because of the ground state, so you can indicate the quantum number is 0. So that is your ground state. Now we can write out exactly. So this is the general expression. So you have the n related with the normalized normalization constant. Then the second component is your polynomial function. Then the third part is your Gaussian function. All right. Now, if you take a look at this, it gets more complicated. This normalization constant is different for different quantum states. And that's why it has a notation of S and B. All right, now let's dissect that one. So the normalization constant also depends on the quantum state. So the general expression equals to the root of 2 raised to the power of b. Then what is this, guys?
Factorial.
Factorial. Okay, good. All right. And then you have alpha over pi raised to the power 1 over 4. So even the constant term also depends on your quantum state. All right, now for the second component in a solution for the wave function, it is a polynomial function in x. Now in math, one trick we always do is substitution. So y here is not the y-axis. It's just a substitution for x. All right, now why we do substitution when you learn in the math? Why we are doing that? It's just to make the expression easier to look, right? Otherwise, it's very daunting. So that's about it. Okay, so you substitute it, you have a variable in x, the motion is in the x. So this should all have x here. But if I plug the x, the expression looks crazy. So I do a simple substitution. That's about it, nothing fancy. So what is the relationship between the x and y, guys? So x equals to, or since this expression is in terms of y, you can return to the x relationship with x divided by alpha. So here you have a y here, but the y can be returned back with your x variable using this expression. Now you can look, alpha is a constant. Alpha equals to h bar squared over m, which is the mass for the oscillator, times the spring constant, okay, and then raised to the power of 1/4. So that it is. So you can return back to the x variables by substitute that. Then we can take a look, similarly, for this polynomial, you have a different expression. We can continue going on, but we only give you the first 7 states. Based on the relationship under the table, you can generate the remaining as you wish. But right now, the textbook gives you the exact expression for the first 7 quantum states, when the v equals from 0 all the way to 6. All right. Now, when it's in the ground state, what is the expression for the polynomial term, the HV?
1.
Is 1. Okay. Now, the last part is the e function. E raised to the power is it, negative decay to the negative y squared over 2. Okay. So that is the solution. How do we get that? Is from the Schrodinger equation, solving for the Schrodinger equation. Impose the boundary. You use your mass scale, and that's how you solve for it. Okay. Now, for us, we have an oscillator. We want to predict properties. In order to do that, then we need to have an exact expression for that quantum state. So let's do some practice. To write out, this is a generic solution. Now we want to write out the exact quantum state. Now, in exam, if I want you to calculate the average position for the quantum state v equal to 6 versus quantum state v equal to 0, mathematically, which one will be easier?
0.
Zero. Okay, so I will not ask you guys to do with the constant state at 6, but we need to figure out how to write out. Okay, so let's practice. So we want to write out the constant state at 0. Okay, now let's try it. So I will have the constant term, so which is 1 over root 2 raised to power 0, right? And then you have 0 factorial, and then you're going to have alpha over pi 1/4. What would be this value here?
It's 1 times 1. This is just 1.
This we know is 1, right? Okay, so let's. So first of all, everybody knows how to do factorial? Okay, so let's say, okay, if that's the case, what is the value for 5 factorial?
5, 4, 3.
Okay, very good. Alright, okay. So that is your constant term. Okay, you can keep it alpha right now for simplicity. You can replace it, and then what do you have for the HB? 1. And then you have the alright. Okay, now I'm not done yet because this is in the variable x. So what I have to do is, let's do this. Instead of y squared, I'm going to substitute the y. Maybe write larger so you guys can see it. Right? So you write it in terms of x variables. You have a constant term. You have the HB. Then you have the e function. You want to return everything in terms of the x variables, and that's what it looks like. Now I got to try the quantum state. Alright, I'm going to give you guys a couple minutes and practice that. I think you can write in terms of alpha, which is fine. As you're starting to write out, you can substitute it toward the end as you wish. Alright, let's do it. Alright, so let's go through the constant term. So this is the wave function. You have a quantum number at the subscript to indicate the quantum state. Make sure you carry the proper variables. And then for this vibrational motion, you have a constant term. So 2 raised to the power of d equal to 1. Then you raise to the 1. Then you have this factorial term right here. Now this doesn't change no matter the constant state you are having. Now you need to look at the HB equal to 1, which is 2y. Y is x divided by alpha. Right here, you substitute in. And then the same thing. You're going to have that Gaussian function component. Alright, and then you can do the same for the remaining constant state. Alright, now once we have the exact wave function, it's a mathematical function, you can plot with respect to the x. Now we said this is a solution. So we define the quantum state through the boundary condition. Of course, this keep going. Now what is the range for the x? That's my variable. What is x?
Position.
Displacement. It's not it's a displacement. And the displacement can be from realistically or ideally can from positive infinity. Okay, in that case, you have a mathematical function. You can define a particular quantum state. You can plot against your x x variables, and then you're gonna have this shape of your wave function as showing here. So this is showing you the density. Okay, so when we talk about density, let's go back to the chapter 1, the postulate for quantum mechanics. How do we define a density? That's density. So we said the wave function. The wave function itself, what do we call it? It's really it's the amplitude, right? Now, density is defined as the square absolute. Okay, there's a square absolute of a particular constant or function. Would it be always true?
No.
Huh? Would the square absolute always true?
No.
And you remove the absolute sign?
No.
Yes or no?
No.
No.
No, right? Oh, 50% of you guys did say the opposite during your exam. Okay, but they're very good. We clarified. So what would be the better way to write this if you take out the absolute?
The complex conjugate.
Yeah. And then you don't skip the step. Then you can say, okay, complex conjugate of a real number, real function equal to itself. Then it will become the square. Okay, all right, very good. Okay, so the density is the square of the wave function, and we plot those ones for your the wave function itself as the red curves, and the density in terms of the blue curves. Here it directly is c squared because this wave function is a real number. So if it's a real number, the square, absolute just equals to the square of that function. So in that case, look at the shape. Where will you locate the maximum for the density? It is at your x equal to 0, which means at your equilibrium point. Okay, now, what if you're looking at, so basically it's more likely to look if the system is at the if the system is at the ground state. I think that's the ground state solution. All right, now what if the wave function is the first excited state, which b equal to 1, then your maximum for the density is at different location, and how are you going to solve for that? It's just find the maximum for this expression. That's about it, okay? And then you can continuously go on. All right, then we can impose, we can dissect a little bit the multiple sets of the wave function. Did you guys see the blue curve right there in that diagram? That blue curve? What is that blue curve? There's so many things in that one plot. There's so many things in that one plot. Did you see the blue curve? Of course, the axis is the variable motion displacement in the x-axis, okay? Now, in the y-axis, impose the energy for different quantum states, but that quantum state is defined within the blue curve. What is the blue curve, guys? Well, what is the potential for this vibrational motion? The potential energy. Is it potential for the harmonic oscillator, 1 half kx squared. To the blue curve indicating the potential well for that oscillator. It's a parabolic and has a value of 0 when x is equal to 0, but it's symmetric from the negative to the positive x. Okay, and then we encode the energy for the system within that potential well, as you can see. And the indicator from the on the right side is your quantum state, y-axis. On the left side is corresponding energy imposed onto your potential well. And then showing the red color is the wave function what look like. All right, so now you can see the wave function is more curly as you increase your quantum state, and then you can see the you're gonna have a different maximum for locations as the system in different quantum states. Now we say when we're solving for this Schrodinger equation, we need to impose the boundary. What is the boundary balance for this particular system? Boundary condition. This is our potential energy. So which means this guy going to approach to infinity. Let's just do infinity as x approach to the two ends. So that means, the particle will be trapped in the potential well as the system approach to the limits. You guys follow me, okay?
Mm-hmm.
Right. So in that regard, for that to be realized, as you guys can see, the component for the Gaussian function, the E function here, goes very strongly to 0, of course, as x approach to larger values, and that will satisfy your boundary condition. I hope you guys understand why we have various components in this solution for the function is to really first to match with the differential equation. Second is to satisfy this boundary condition. So the first thing is to make sure the wave function approaches to 0 at these two edges of the potential well. All right, and then the wave function decays more rapidly for large mass and the stiff springs. Yeah, of course, because in that E function, you have the alpha term right there, and the alpha is related with your mass of the oscillator and the spring constant. So therefore, if you're looking at different oscillator, you can compare that wave function decays differently, depends on the spring constant and the mass for the oscillator. Okay, now the third one conclusion we can draw is the wave function can spread over a wider range as the quantum number increases, right? You see how that spread out? Okay, I think I'm gonna go one more slide. Just want to make sure I have enough time to go later. So this we can take a look at the density. The density is just the square absolute. Now if you take a look at it, you guys can see what the maximum is going to look like at different quantum state, at the ground state versus the higher excited state. Have you guys seen this? Do you guys have an old clock like that go back and forth and
Grandfather clock?
what do you call that?
Grandfather clock?
Grandfather clock.
Yeah, no, I when I was really young, I had one at home like really big, like this big and sits on the floor. And then with technology evolved, I digital get rid of it. Now I regret it. We should have kept that one and save a lot of money, right? So it would be ancient anyway. So now you can think about that motion, right? That kind of a motion. Right. Now the square of the first few eigenfunction of the quantum mechanics harmonic oscillator, we simply impose onto it. As you can see, here has a higher density toward the edges of the, so it's more likely to locate the harmonic oscillator at the edges of the wall, okay, potential wall. All right, now, for classical and quantum mechanics, they converge. If you look at a higher quantum number. So I think I'm going to end it here, and then we come back on Friday. Is now we know the solution for the wave function, we know the solution for the energy. Now, can we solve some of those problems as we listed here? Okay, all right. All right, as I have mentioned, I would like to go through this because this is the root of our class for the material involved in the exam 1. So all the future lectures, all based on the application of that principle and quantum mechanics. Okay, so now let's go to the first question. I'm not going to give you guys the examination. I'm going to hold it until I'm going through it. All right, because otherwise you guys are going to be so curious. I know you guys are curious. Just let's go through it first, and then I'll hand out the feedback. All right, for the first one, so we say the first thing definition for the description for the postulate is the introduction of the wave function. We say if we have a wave function from the quantum mechanics, we can predict the property instead of going in the lab and solving for the measure experimentally. We can predict. Now, how we're going to predict is for a particular observable, we will have a corresponding operator. Okay. Now, we can operate that operator onto the wave function in some shape and form that will allow us to obtain that dynamic information. Now, we were given with two operators, and we're going to construct the remaining of the operators through those two. So what are the two operators that are given to you? One is your position operator. Now, it's an operator, so it's an operation. So what is an operation for a position operator, guys?
Just
it's
X.
a modification. So if the position is X, then you have an operator for the X position, then you have this variable, and then you multiply. So the operation is multiplication. All right, now how about the second one? I give it to you. Is the linear momentum, right? The linear momentum operator is, let's just say in one dimension, the same for the other dimension. It's a constant, and then on the d over d axis over the line. So it's a derivative. All right, now using these two, and then plus the relationship you learn in physics, we can generate the others. For example, what about the operator for the kinetic energy operator? Let's just say in one dimension x. Then I'm thinking about it in physics. What is the relationship for kinetic energy with respect to the linear momentum or the positions? What is the relationship? Can we generate the kinetic energy with respect to linear momentum or position? What is the relationship? So, right, that's what we learn. That's what we learn from physics. In that regard, if we want to generate the operator, we plug it in. Same thing. So you use two things. From what given, and what the relationship you will learn from physics. And then yeah. Okay, now for this particular one, so you can think about this mathematically. I have this expression, just plug it in. Carry the square. Now, of course, you can do, it does a times b, so you have h bar squared over I squared. Then you have, that's it. And this actually really constitutes the kinetic energy operator. If you think about it, the kinetic energy operator carries this term here, except you need to divide it by 2. Okay, so this is really touch bases about operator, how we can generate operator. Okay, so the number 2, so you have a system. Number 2 is really, okay, now we have a wave function that is important. Now how are we going to generate the wave function? Is by solving the Schrodinger equation. Solving the Schrodinger equation, you need the 2 components. One is you need to generate the Hamiltonian operator. Number 2, you need to figure out the wave function with corresponding variables. So therefore, you will be able to solving for that Schrodinger equation. Does that make sense? So therefore, if you have a system with 2 particles, then you need to define the position for each of the particles. If it's moving in, I know in one of the slides we have this particular problem. So the system have 2 particles. Now we need to have a position vector that is R1 and R2 that each define the position for each of the particles. Now this is moving in 2 dimension, then your position vector will become does that make sense? So for that particular problem, all you need to do is those 4 variables. Alright, I think in one of the lecture notes we have more examples than this guy right here. Okay, then once we know these variables, because we need to have a variable for the wave function, we generate a Hamiltonian operator, then we can solve it. So that's the starting point is, for a particular system, you need to know how many particles, whether they move in 1 dimension, 2 dimension, 3 dimension. For each of the particle, you need to have a position vector, 1 or 2 or 3D dimension, depends on you how many x, y, z you want to have. That's not it. For us, this problem, we have 2 particles, so you have 4 variables. All right. Now, one of the postulates is regarding with the Schrodinger equation, how to generate the Hamiltonian operator. Then the Hamiltonian operator, we have been talking about the whole time. We will continuously discuss about this through the lecture. It has 2 components. Right? In general, it has 2 components. What are they, guys? You have kinetic energy plus the potential energy. For this particular problem, do we know the potential energy?
0.
It gives you, now it's a multiplication. All right, now how about the kinetic energy term? Okay, now if a system has many particles, then the energy of that system for kinetic energy is just a sum of each one of them. So in that regard, the kinetic energy term will have components from particle 1 and from the particle 2. Okay, now I have a solution here posted, so therefore I'm not going to go anything further. But if you have 3 particles, then your kinetic energy will have 3 three component. You may have multiple potential energy terms as well, but this one only tell you I only have one term. Okay. All right. The question of number 3 is really relies on the normalization. So how do we normalize a wave function, guys? Is the integral of this is true. That is your normalization. Of course, you can add the proper limits, plug in the right wave function, understand the dimension, whether it's a 1 dimension, 2 dimension, 3 dimension, and the rest really rely in the mass operation. Okay. I think the B is directly from your homework assignment. Okay, so the question C. The question C asks you, we have an operator, we have a function. Which postulates this problem touches bases on? Huh? It's on the eigenvalue and eigenfunction, right? And then also touch bases on the operator onto the wave function. All right, so now I have an operator in general onto the wave function. This is a mathematic operate. Of course, it execute on something. The order is like this. Do you guys think this is the same?
No.
Not necessarily.
Huh?
Not necessarily.
This is not the same, right? Because you have operation operate onto nothing. All right, so let's clarify that one. Okay, now if we operate here, we have the derivative, which is that's your operator. Operate onto the wave function, which is the function. The function is e to the ax squared. That's it. We have operator onto the wave function, directly plug it in, and this is. Now I'm asking you, if you have a minus b times c, mathematically what do you do? You have AC minus BC is your distributive property. Okay, now let's apply to this. Now what do we have? This is your A. This is your C. Now this is a minus sign. You guys all following me, okay? Okay, now this is a second order derivative with respect to this guy here. So now let's do the first one. What do we have? After we come off the first one, I think we practiced something.
Negative 2x.
What do we have here?
-2ax.
So you use the derivative with the e function, but then you need to use a chain rule. So there's the two things involved. For the chain rule, okay. Now again, if you do a derivative with this one, what do we use? You have a chain rule, you have an e function, what else? Product, so you can use three of them. Three of them, right? Okay. Make sense? You use three of them, then you have a solution. Then once you have a solution, then how are you going to say this is an eigenfunction or not is whatever the thing you found in your wave function has to be a constant. In that case, anything related with x has to vanish. Okay. All right. Okay, so the last one. Oh, I still have time. So some of you are clean up, but then, oh, no, that's not yet. Okay, for the last one, if we take a look at this, again, we check the eigenfunction, eigenvalue. For the first one, it's really straightforward. Yes, it is an eigenfunction. If you have a linear momentum operator operate onto the wave function, you're gonna realize that it's an eigenfunction. For the second one, we say the probability density. Is this your probability density?
No. Wait.
Is this? Oh, this, whatever.
Yes.
That's your probability density? Oh, I hear different things. We said this is your amplitude. This is your
Probability.
probability density. This,
Oh, that's the probability at a point?
probability at one point.
Oh, okay.
Amplitude, probability density at one point, probability at one point, and then your integral, that calculate your probability within a
Range.
variable. So some of you stumble here is just conceptually using one of the expressions. Okay, now all you guys are looking forward. Can I tell you guys